This is question number 5 from the 3.3 notes on product rule and quotient rule for derivatives. So in this problem, we're given a function that's a quotient. There's the function x in the numerator. And in the denominator, we have a function that's a binomial cube. So I'm going to start organizing my work. I'm going to find the derivative of the top function. So if the top function is a plain old x, the derivative of a plain old x is just 1. And my bottom function, when I take the derivative of that, I'm going to need chain rule. I'm going to do power rule. But since my base is, in this case, a linear binomial, I'm going to have to tack on the derivative of the base when I do my power rule. So I drop my exponent down to the front. I rewrite the base exactly as it's given to me. I decrease that exponent by 1, and then I tack on the derivative of the base. Well, the derivative of my base is just 2. So let me go ahead and write that out. This is in the form y equals mx plus b. I can see it's linear. We know that derivatives are just slopes. So the slope of this function here would be 2. So the derivative of that is 2. Or you can apply the power rule. However you see the derivative there. The derivative of the base is 2. And then when I clean this up just a little bit more, that's going to give me what? Order doesn't matter when I multiply. So 3 times 2 is going to give me 6. And then I'll write my binomial square there. Okay, so now that I have all those pieces worked out, I can apply them, put them into the template. So my derivative is going to be the bottom, okay, the bottom right there. So let me write that out. Binomial cubed times the derivative of the top, which was just a 1, minus the top, which was an x, times the derivative of the bottom, which we simplified right there. So 6 times the binomial squared, all over the bottom. So I'm coming back up here to the bottom. It's hard to read now. Let me take all that shading off. The bottom was a binomial cube, and the bottom gets squared. Okay, so this is your raw derivative. In part A, if they're just asking us to find f prime, I could type this raw derivative into my MATLAB exactly as I've written it, and my MATLAB will count it right. However, we're being asked to do part B, which is to find the values of x where the tangent line is horizontal. So we definitely want to clean up this derivative before we even attempt part B. So let's go ahead and clean this up a little bit. Okay, so cleaning this up, I'm going to go ahead and multiply the bottom times derivative of the top. That's just being multiplied by 1, so it's the binomial cubed, minus, going to clean this up here a little bit. The only thing I can really do is write the 6 first, the x second, and then my binomial square. Okay, and all of that's over the bottom squared. So if I have 3 binomial factors and then I square it, I do it twice, that's going to be 6 binomial factors. The exponent rule, power to a power exponent rule, is to keep the base and multiply the exponents together. And this is pretty yucky. Like if you tried to do the algebra on this, you would have to write the binomial factor out 3 times minus 6x times the binomial factor twice and do all kinds of algebra. So what we can do instead to clean this up is ask yourself, is there a GCF? Is there a GCF in the numerator? GCF in numerator? So the calculus is over. I'm just asking myself, is there a GCF between this first group and the second group? And I can see that both groups have the binomial factor in it. The first group has the binomial factor 3 times, and the second group has it twice. So yes, there is a binomial GCF I can factor out. So let's go ahead and do that in the numerator. So my denominator is going to stay exactly the same, so I'm going to rewrite it. But in the numerator, I'm going to factor out a binomial square, and let's see what gets left over. So in this first group, if I factor out a binomial square, if there are 3 factors of the binomial and I factor 2 of them out, that's going to leave me one of the binomials in there. And the parentheses are optional because If there's only one left, it's an understood exponent of 1, but we don't write that because it could look like a prime. So I'm just going to write the binomial without the parentheses. And then in the second group, I'm factoring out both factors of the binomial. So I'm just going to be left with a minus 6x there. And then I can clean that up if I want. So let's, inside these, inside this set of brackets, there's some like terms there. So let's go ahead and clean that up. So what will that look like? Okay, I'll write it down here. Okay, so I would have the binomial squared, and in the brackets, I would end up with a negative 4x minus 5. I can write that as parentheses if I want. And all that's still over my binomial to the 6th power. And I can keep simplifying because now I can see that in the numerator, I have 2 factors of the binomial, and in the denominator, I have 6. So 2 of them will divide out. So 2 of my binomial factors in the numerator will cancel out 2 of these and leave 4 of them in the denominator. So what I really have there is a negative 4x minus 5 in the numerator, and then my binomial to the 4th power in the denominator. So this is my simplified derivative. That is my simplified derivative. And this is going to help me solve part B, which is asking me to find the values of x where the tangent line is horizontal. And again, all of this was algebra that we did. So the calculus stopped. Let's see, where did the calculus stop? The calculus stopped here. The calculus stopped here. So the calculus was when I was taking the derivative of the top and the derivative of the bottom, and I plugged them into the template. That was the calculus. Everything else I did after that was algebra. It was algebra I was doing to simplify. So all this is algebra that I was doing to simplify my derivative. It got the simplified derivative. So now let's look at part B here. Let's talk about where the tangent line is horizontal. Well, if a line is horizontal, that means it has a slope of 0. We know that from algebra. So that means the derivative would be 0. So all I'm going to do is set this derivative that we just found in part A, this simplified derivative. I'm just going to ask myself, what values of x could I input into this derivative that would create an output of 0? Okay, so for a fraction to be 0, we need a 0 in the numerator and any other non-zero number in the denominator. That's going to make it a 0. So I'm just going to focus in on the numerator being 0. What values of x would make the numerator 0? And as long as that value of x I find does not make the denominator 0, we're good. If it makes the denominator 0, we have a problem, right? But if it makes the numerator 0, then the derivative will be 0. So all I'm going to do is set that numerator equal to 0. So let me go ahead and do that up here since I've run out of space. So I'm just going to set that numerator equal to 0 and solve for x. I'm going to add 5 to both sides. I'm going to divide by negative 4. So if x is equal to this negative 5/4, so if that's what x is equal to, if I plug that x into any of these derivative forms, they're all equivalent, right? They've just been cleaned up with algebra. If I plug it into any of those, if I input negative 5/4, or what is that, negative 1.25 into any of these forms, the output should come out to be 0. So that means the tangent line would be horizontal at this x value. And I know that's not a pretty number, but just think big picture ideas. What do I know from algebra about a fraction equaling 0? Well, that means the numerator has to be 0. The denominator can't be 0, right? And if I look here, plugging 5/4 into this denominator would not make the denominator 0. So we're safe. So yeah, we're done. We found the raw derivative. We used algebra to simplify that down as much as possible. So then we could do part B where we found where the tangent line was horizontal and we know the x value that's going to create that output of 0 in the derivative. Okay, as always, email me if you have follow-up questions.